Assessment. Good morning, everyone. I'm from the University of Melbourne. I'm going to be talking about a biophysical perspective of IPCC integrated assessment modelling. So my talk's going to concentrate on the treatment of economic growth in IPCC integrated assessment modelling. IAMs are the main scenario modelling tool. So these form sort of the backbone. These are the mainstream process by which the IPCC generates scenarios. I'm going to be talking about the Kaya identity because this is a key part of the way the modelling is done. I'm going to offer a biophysical perspective, show you a proposed conceptual model, which I'll touch on briefly, and then wrap it up. So if we imagine, we're sort of trying to think about how we're going to model future emission scenarios in the world with anthropogenic emissions, with the carbon cycle and everything else going on. It's a very difficult thing to do, and I think one of the things I really want to emphasise that if you're sort of starting from scratch, it's a very difficult thing to do, and the alternative is to basically do nothing. And so one of the key points I wanted to make was that although I'm going to be critiquing the way the models are done, if you're starting from scratch, it's actually a very difficult thing to do. And so the solution to this is to use integrated assessment models, which are highly simplified, stylised numerical models. The key thing is that they integrate the main parameters of interest: energy, agriculture, carbon cycle and the economy. But one of the problems is they use economics as a basis for decision making, and it's a type of economics which is standard economics. And critically, they're driven by exogenous scenarios, and that's the thing that I'm going to be concentrating on in the first half of the presentation. Okay, to start with, if you're thinking about how you're going to develop scenarios, what are the sort of drivers of scenarios? And these are some of the things. This comes out of AR5, the Fifth Assessment Report. These are sort of all things that make sense: behaviour, trade, resource availability and so forth. But it's very difficult to model all of those things. How do you bring all those things together? And so, and these are the underlying drivers. And the way that these things are brought together is to bring them down into four, to determine the drivers of greenhouse emissions, to bring them down into four factors: population, projections, the intensity of energy intensity of energy production, the energy intensity of GDP, and GDP per capita or wealth. And so they're immediate drivers. Now, a lot of you will recognise these four factors as a Kaya identity, and that's what I'm going to be discussing. So if you look at the top half of this image, this is to illustrate that there's been 5 main families of scenario modelling starting in 1990. The SA90 family was a pretty basic model based on energy mix and efficiency. The 1992 family, IS92, included population, income and fossil resources. But it was really the SRES that was introduced in 2000 that introduced the Kaya identity. And the current scenario modelling is the SSPs that was touched on earlier. So the Kaya identity is pretty simple. CO2 emissions are a function of population, GDP per capita or wealth, energy per unit of GDP, which in other words the energy intensity of economic activity, and the carbon intensity of energy. So that looks pretty basic, and it comes about from the earlier IPAT identity. Many of you will know this from Ulrich and Holdren. Impact equals population times affluence and technology. But these two, conceptually, these are two different types of equations. IPAT was intended as a formula. It was a stylised formula, but it was intended as impact was the dependent factor, and the right-hand terms were independent. Whereas the Kaya identity is, and I'll move on to that in the next slide, it isn't exactly the same thing. And we've got, there's the issue of, these are descriptive equations, and what has sort of happened is that Kaya has sort of taken on a type of IPAT role, which it was never intended to do. The key thing about an identity is that the same term appears on the left-hand side and right-hand side. CO2 is on the, it looks like the dependent term on the left-hand side, but it's also on the right-hand side. And the rest of the terms simply cancel out. So, I mean, this is what an identity is. And it's meant to be a useful decomposition tool. And when you first see it, it sort of makes a lot of sense, because all of these factors, they're measured, they're known with fairly good accuracy, they're known at a national level and an international level, and there are ways to think about drivers of greenhouse emissions. The problem is it's not a causal relationship, but it's taken on a role of a causal relationship, even though from SRES in 2000, there was actually a section devoted to talking about how it explicitly wasn't a causal relationship, but it was a way of decomposing the terms to develop future scenarios. But over time, it's kind of taken on a life of its own. And the second equation there, I've simply taken GDP out. So you can do that. You can add or subtract whatever terms you like. And if you take GDP out, what you get is simply energy per capita. And if you look at the second equation, it kind of frames the debate in a quite different way. It's about our individual energy use per capita, rather than thinking about how wealthy we are. And I'd argue that the power of Kaya is it supports a techno-optimist framing. It supports a particular type of framing. Wealth is compatible with abatement, providing carbon intensity asymptotes towards zero. And I think this is a key way that the debate has evolved. Now, and I'll talk about it the next few slides, but if we look at GDP population, in the modelling, this is an exogenous term. It isn't a feedback term, it's simply plugged into the numbers. And if you just plug in increasing wealth, it drives, you can assume that wealth just rises spontaneously. And so if we have rising energy efficiency combined with renewable energy, the result is we just need more technology to reduce CO2. And this is, to me, what really comes out of the Kaya identity. It's not the only way of looking at it, but I think it's the main way it tends to be framed. Now, one of the features of this type of equation is that at low deltas, we can simply add the terms on the right-hand side to give our percent change. So it isn't an exact equation, but it works out at low deltas. And so if we look at from 1970 to 2016, these are the way the figures come out. Now the left-hand side doesn't equal the right-hand side. They're only approximate because I took each of these figures independently and I plugged them in. So you can see that's this is the annual average change since 1970, 2% increase in CO2, which is driven mainly by population and increase in wealth. Meanwhile, energy intensity has been falling, and there's been a slight decrease in the carbon intensity of energy. But interestingly, since about the mid-90s, there's been virtually no change in the carbon intensity of energy. So this is historic change in world GDP per capita. If you look at that, you might sort of get the feeling that energy has sort of something to do with world GDP per capita. One of the main things is that post-1970, it's averaged about 1.4%. And so this is the same data, except with constant 2010 US dollars. Now, we should get this type of equation, we should get sort of something of an exponential, but because we get all these drops, it ends up being more of a linear equation, a linear line, sorry. So the next graph I'm going to show starts at 2010. So I've just put that dot just to mark that as a reference point. So in 2010, the average GDP per capita was about 10,000 US dollars. Now I'm going to show you one of the current SSP scenarios of GDP per capita. This is from Dowling, and they've produced 5 scenarios. Well, sorry, there are 5 scenarios, and this is the results. Now, one of the features of the scenario literature is that probabilities aren't attached to each scenario, but they're all considered plausible. Now, you're probably interested in SSP5. So this is using 2005 US dollars. This is what the scenario comes up with for average GDP per capita. So you can make your own decision about the plausibility of those figures, but I mean this is what the scenarios are saying. So that equates to about a 14-fold increase from 2010. The bottom one is about, what does that say, 2 to 3-fold increase. So if we just take that 1.4% from the previous graph and overlay that, that's where it comes out as, at sort of at the bottom end. So once again, with these scenarios, there isn't probabilities attached to them, but they're all sort of put out there as being plausible scenarios. So what I'm going to show next is I'm going to combine the 2 right-hand most of the Kaya identities on the y-axis. So that's the change of carbon emissions per unit of GDP. So that combines the energy intensity of GDP and the carbon intensity of energy. And then on the x-axis, it's simply the change of per capita GDP. This is based on a graph from derived. So this is the first scenario series from 1990. So this was a pretty sort of basic scenario, and they just said, okay, we'll just assume that income's going to grow 1.5%. These are different scenarios. The top one was business as usual. So that was pretty simple. Then in 1992, it got a little bit more sophisticated with changing income growth and a range of changing carbon emissions per unit of GDP. Then in 2000, the SRES scenarios introduced a much more sophisticated way of doing it, and this is where the Kaya identity was introduced. And you can see a much broader range. So if we look at actual post-1990, that's where it's been. So it actually looks like the 1990 scenario was actually pretty close to where we are. And then you can make up your own mind as to what the other scenarios really mean. Remembering that the scenarios aren't projections, they're simply what-ifs. And with the IPCC scenario literature, often we've got to differentiate between sort of scenarios and projections because they sort of take on a life of their own. The scenarios become almost as though they're projections, but they're not. So the next thing I'm going to put on the graph is the SSPs. So this is the SSP baselines. So formulation of these started in 2014. And so what you can see is that they're similar to the SRES scenarios. And this is one of the SSP mitigation scenarios. So this is one of the stronger mitigation scenarios. And one of the main things is that the green dots simply move down because the change of per capita GDP is just simply given as exogenous. It's not a feedback term. A change in energy system effectively has no change on income per capita. This is part of the way that the scenarios are done. So that dot simply moves down. Actually, on these, they're more shaded on my thing, but that doesn't actually matter. Now, I don't know whether you can see, but these are 2-degree scenarios out here. And actually, they're dependent upon strong economic growth. So, I mean, this is the way the scenarios work. No laughing, girl. Now, one of the interesting things is that the carbon intensity of energy hasn't changed much since, well, I put since 1990, since the 1990s. So with the y-axis, all of that change has been an improvement in the energy intensity of GDP. It hasn't been in the carbon intensity of energy. And historically, the per capita GDP growth has been at the lower end of projections. So the question is, what is driving the drivers of GDP per capita growth? Where do these numbers come from? And the papers that are doing this, well, Delink is actually, they're a group from the OECD. They use the EMB growth model. And the first thing they use is they look at demographics and labour participation. So simply, as population ages, as demographics change, you have more or less people working. Then the main driver is multi-factor productivity growth. So they call it labour quality, we can call it human capital or education. As people become more educated, it's an assumption that income per capita will grow. There's an improvement in capital quality, but really the main driver is what is called pure technical progress. Solo's technical change, it's just this exogenous driver. We get better at doing things, and this is the main driver of economic growth. There's also political factors. There's an assumption of what is called convergence. So developing countries will get wealthier. The difference between the developing and developed countries will converge. There is kind of a political necessity to do that as well, and this enters the model. So if developing countries have much higher economic growth, this then adds to the overall world economic growth. So I'm going to try to sketch the way I think about it in terms of a biophysical perspective. So this is a model, this is a diagram from Paul Samuelson text. This is a circular flow economy model. This is the way that standard economics thinks about things. We have producers and purchasers. We have the flow of money in terms of consumption purchases. We have wages, rents and profits, etc. Now, the figure I put there is world GDP at the moment, about 76 trillion. Now, one of the features of GDP, the way that GDP is calculated, is that it's based on effectively double entry bookkeeping. So the top figure is essentially calculated from expenditures, and the lower one is calculated from income. And so income overall equals expenditures. The beauty of this is that everything just goes round and round forever and ever, and there's no loss, and this is the way that standard economics thinks about things. And sort of up to a point, it's okay, but it's not without its problems. And so within that model, energy supply is just one sector. It's not a particularly special sector. It has a role to play, but it doesn't have a particularly special role. And then as far as energy and materials, waste and pollutants, they're simply external to the system. You know, if we decide to price pollution, we do that within the framework of the main system. And energy and materials, it's really just the capital and labour that we need in order to extract them. Otherwise, they're basically available for free from nature. And so the main driver of this, of productivity growth, is explained by Solo's residuum. It's technical progress. We just get smarter, we get better, and it just happens. But this is the way I think about it, by a physical way. We have primary energy from nature, which is processed by energy supply industries, which produces commercial energy. So we have primary energy, goes through, is converted to commercial energy that can be sold, which is consumed by end users and industrial use. And this is how I think about EEIOA. It's simply the ratio of the total commercial energy out divided by the commercial energy that's used by the energy supply industry to produce energy for society. So primary energy from nature doesn't enter the EEIOA equation. So whether we're harvesting, say, sunlight, wind or coal, from this perspective it's all treated the same from an EEIOA perspective. And then just drawing some neat boxes around it, we have reserve potential energy from nature, goes through a dissipative system and then ends up in the environment which has a low potential. So it ends up as low-grade heat. And so this is just a thermodynamic perspective of how the economy operates. And so to contrast the standard economic with the biophysical model, this is the way that I think about the major differences. So we have a circular versus a linear system. And so this is a sort of a fundamentally different way to think about it. We also have a closed versus open system. Now, one of the features of closed systems is it's much easier to get equilibrium. It's much easier to get stable systems. In a mathematical sense, systems have stable points, equilibrium, whereas open systems are much more likely to be unstable. So from a standard economics perspective, technical progress is the main driver of economic growth, whereas from a biophysical perspective, it's increasing energy quality. So from a standard economics perspective, economic growth just happens, whereas from the biophysical, economic growth is an emergent property of the system. You can't just plug it in as an exogenous figure because it just doesn't make sense. And so using this, it can only be understood at a macro scale. I think one of the problems with this type of work is that if you try to drill down at a national level or at a regional level, there are lots of different things happening, and particularly with globalisation, you can find it doesn't work as well. This type of system really needs to be understood at a global level. And so globally, 76 trillion US dollars is sustained by about 18 terawatts of power flows, and it's as simple as that. So this is from a paper I recently published. This is my proposed conceptual model to try to address this issue. I think it's more of a band-aid type approach, but this is the way that I think about it. So we have an integrated assessment model on the left, which produces an aggregate output. So that has to be converted into a detailed energy system model and modelled input-output tables. I've looked at this way because I've done some environmentally extended input-output modelling, and I think that can give really useful results. This type of model would be very difficult to actually do in practice at sort of anything like a global level, but I'm offering it up anyway. And so what we end up with is a scenario-based environmentally extended input-output model. And the really difficult thing is thinking about what should be in a transfer function which converts EEIOA energy cost share into GDP growth. And I think this is, if we could come up with a really good transfer function, that would be really useful. And so conceptually, this gets fed back in as a negative feedback into scenario modelling of integrated assessment models. The idea being that if the integrated assessment model produces results that just don't make sense, this type of model would actually pick it up. And so just to wrap up, Kaya and standard economic assumptions lead to biased framing of energy transitions. There is kind of a standard way to think about energy transitions, and I think that the way that Kaya is used, it tends to lead to a particular way of thinking about it. So the biophysical perspective is that productivity and economic growth are in fact emergent properties from the system. You just can't plug in numbers. It makes no sense to just plug in numbers. And so the standard economic modelling approach does not capture the energy economic nexus. But I think we all need to work harder to come up with really good models that are useful, that are predictive, and that can make a better contribution. Thank you.